The cosmic horizon, also known as the particle horizon, marks the boundary of our observable universe. It represents the maximum distance from which light has had enough time to reach us since the beginning of the universe. Beyond this horizon, there are regions that are simply unreachable to us because the light emitted from those regions has not had enough time to travel to us. To understand this concept, let's consider the age of the universe. Currently estimated to be around 13.8 billion years, this is the amount of time that has passed since the Big Bang. Light travels at a finite speed, and in the vacuum of space, that speed is approximately 299,792 kilometers per second. So, over the course of 13.8 billion years, light can travel a maximum distance of about 13.8 billion light years. Now, imagine a galaxy that exists at a distance of, say, 15 billion light years from us. Light emitted from that galaxy would need more than 13.8 billion years to reach us, which means it hasn't had enough time to do so yet. Therefore, this galaxy lies beyond our cosmic horizon, and we cannot observe it directly. It's important to note that the universe has been expanding throughout its existence. As space expands, the cosmic horizon expands along with it. However, the rate at which the universe expands is not uniform, and it has changed over time. This means that the distance to the cosmic horizon is not simply 13.8 billion light-years multiplied by the current age of the universe. The expansion of space also affects the motion of distant galaxies. Galaxies that lie beyond the cosmic horizon are not only unreachable to us, but are also moving away from us at velocities greater than the speed of light. This might sound contradictory, as nothing can travel faster than the speed of light within space. However, it's important to understand that the expansion of space itself is carrying these galaxies away from us, rather than their actual motion through space. As a result, galaxies beyond the cosmic horizon will never reach us, no matter how long the universe exists. The expansion of space causes the distance between us and those galaxies to increase continuously, leading to a point where the distance becomes so vast that the light from those galaxies will never have enough time to reach us. While we are limited by the cosmic horizon in terms of direct observation, scientists can still study the effects of the distant universe indirectly through various cosmological observations and measurements. These observations help us understand the large-scale structure of the universe, the distribution of galaxies, and the processes that have shaped our cosmic landscape. Redshift occurs when electromagnetic radiation, such as visible light, undergoes a change in wavelength. As the universe expands, the space through which light travels stretches, causing the light waves to elongate. This stretching leads to an increase in wavelength, resulting in a decrease in wave frequency and photon energy. In the case of visible light, this shift causes certain elements' absorption lines to move towards the red end of the spectrum, hence the term redshift. To understand the significance of redshift, let's consider how it helps us gauge the expansion of the universe. As light emitted from distant galaxies travels towards us, it encounters the expanding space in between. The further the galaxy, the more space the light must traverse, and consequently, the more pronounced the redshift becomes. By measuring the amount of redshift in a galaxy's spectral emissions, scientists can determine how much the universe has expanded since the light was emitted. To quantify this expansion rate, scientists employ the Hubble constant, which represents the rate at which space is expanding. Currently estimated at around 65 kilometers per second per megaparsec, the Hubble constant tells us that for every megaparsec, equivalent to about 3.2 million light-years of distance between us and a galaxy, the space between us and that galaxy is expanding, causing it to move away from us at an increasingly faster rate. It's important to note that the concept of redshift also highlights a limit to our observations. As the universe expands, there comes a point where the recessional velocity of galaxies exceeds the speed of light. However, this doesn't violate the laws of physics because it's the space between us and the galaxies that is expanding, not the galaxies themselves. This expansion creates such vast distances that light emitted from galaxies beyond a certain threshold will never reach us, placing them beyond our cosmic horizon. The Hubble constant, named after the renowned astronomer Edwin Hubble, represents the rate at which space is expanding. currently estimated to be around 65 kilometers per second per megaparsec. This constant tells us that for every megaparsec of distance between us and a galaxy, the space between us and that galaxy is expanding by 65 kilometers per second. But what exactly is a megaparsec? A megaparsec is a unit of distance used in cosmology, equivalent to about 3.2 million light-years. It provides a convenient measure for the vast distances between galaxies. The larger the megaparsec value between us and a galaxy, the more space there is between the two, and the faster the galaxy appears to be moving away from us. This brings us to the concept of recession velocity. As the universe expands, the space between galaxies stretches, causing them to move apart. The recession velocity of a galaxy is the rate at which it is receding from us due to the expansion of space. The farther a galaxy is from us, the greater its recession velocity, as it has to traverse more expanding space to reach us. By measuring the redshift in a galaxy's light spectrum, we can determine its recession velocity. Redshift indicates how much the wavelength of light from a galaxy has been stretched due to the expansion of space. The greater the redshift, the faster the galaxy is moving away from us. The relationship between redshift and recession velocity is described by Hubble's law, which states that the recession velocity of a galaxy is proportional to its distance from us. The Hubble constant quantifies this relationship and allows us to estimate the distances and velocities of galaxies based on their redshifts. Understanding the Hubble constant and megaparsecs is essential for comprehending the immense scales at which our universe operates. By studying the redshift and recession velocities of galaxies, scientists can paint a picture of how the universe has expanded over time and gain insights into its past and future. To understand causally disconnected regions, let's consider the vastness of the universe. Imagine two galaxies located far apart from each other, beyond each other's observable universe. Since the universe has a finite age, there hasn't been enough time for light to travel between these two galaxies. As a result, any events or interactions occurring in one galaxy cannot have influenced or been influenced by events in the other galaxy. This lack of causal influence between distant regions is due to the finite speed at which information can travel through space, limited by the speed of light. No information or signal can propagate faster than light, meaning that events in one region cannot instantaneously affect events in another region if they are too far apart. Thus, these regions are considered causally disconnected. Now, let's consider a point within a causally disconnected region. From this point, light can only travel a certain distance within the finite age of the universe, forming the observable universe for that specific location. Beyond this observable universe, there are events and structures that are forever beyond our reach, as their light has not had enough time to reach us. It's important to note that each point in space has its own observable universe. This means that if we were situated at a different location in the universe, our observable universe would differ from what we can currently observe from Earth. The farther apart two points are, the larger the portion of the universe that lies beyond each other's observable universe. As the universe continues to expand, the observable universe for any given point also expands over time. This expansion occurs because the light emitted by objects located beyond our current observable universe will eventually reach us as space expands, making those objects observable to us in the future. This expansion of the observable universe allows us to observe more of the universe's history and gain new insights into its evolution. However, it's important to keep in mind that even though the observable universe expands, the causally disconnected regions remain separate. No matter how much the universe expands, there will always be regions that are causally disconnected from us, forever beyond our reach. One way to estimate the size of the universe is by examining its curvature. According to general relativity, the shape of the universe can be described by its curvature, which can be positive, negative, or flat. Imagine the universe as a two-dimensional surface of a balloon. If the surface curves inward like the surface of a sphere, the universe has positive curvature. If it curves outward, it has negative curvature. And if it doesn't curve at all, it is flat. Scientists have extensively studied the cosmic microwave background radiation, a faint afterglow of the Big Bang, to gain insights into the curvature of the universe. By analyzing the patterns in this radiation, they can determine whether the universe is curved or flat. However, measuring the exact curvature and deducing the size of the universe from it is a complex task that requires sophisticated mathematical models and data analysis techniques. Another approach to estimating the size of the universe involves considering the radius of the observable universe. As we mentioned earlier, the observable universe is the portion of the universe from which light has had enough time to reach us since the Big Bang. Its radius, often denoted as r, represents the maximum distance from which light has reached us. The observable universe acts as a cosmic horizon beyond which objects are unobservable to us. However, it's important to note that the entire universe may extend beyond the observable universe. By studying the expansion rate of the universe and extrapolating it backward in time, scientists can estimate the size of the entire universe beyond our observational limits. Additionally, scientists have developed models based on the large-scale structure of the universe to estimate its size. These models take into account the distribution of galaxies and the clustering patterns observed in the universe. By studying the statistical properties of these structures and their spatial distribution, scientists can make informed estimates about the size of the universe. However, it's crucial to acknowledge that our current understanding of the universe is continually evolving. As new observations are made and more accurate measurements are obtained, our estimates of the universe's size may change. Scientists are constantly refining their models and techniques to gain a better understanding of the vastness of the cosmos. To grasp the enormity of the unobservable universe, we must first comprehend the expansion of space. As we mentioned earlier, the universe is continuously expanding, causing galaxies to move away from each other. The expansion is driven by the force of dark energy, a mysterious form of energy that permeates space. As space expands, it carries galaxies along with it, gradually increasing the distance between them. Beyond a certain point, known as the cosmic horizon or particle horizon, the expansion of space is so rapid that light emitted from distant objects cannot reach us within the age of the universe. Consequently, we cannot observe galaxies beyond this cosmic horizon, making them part of the unobservable universe. The cosmic horizon marks the boundary beyond which information, including light signals, is forever inaccessible to us. This means that even if there are galaxies and structures beyond the cosmic horizon, we will never be able to directly observe them or receive any information from them. Now, here comes the mind-boggling part. The observable universe, as vast as it seems, is just a tiny fraction of the entire cosmos. It is estimated that the observable universe has a radius of about 46.5 billion light-years, which corresponds to a diameter of roughly 93 billion light-years. However, the actual size of the entire universe, including the unobservable regions, is believed to be much larger. To understand the potential scale of the unobservable universe, consider this. The universe is estimated to be around 13.8 billion years old. Since the speed of light is finite, light from the most distant objects that could have reached us since the beginning of the universe has had approximately 13.8 billion years to travel. However, due to the expansion of space, those objects are now located much farther away than 13.8 billion light-years. Based on current cosmological models, it is hypothesized that the universe is likely much larger than the observable universe, potentially spanning a staggering expanse of hundreds of billions or even trillions of light-years. This suggests the existence of countless galaxies, star systems, and celestial phenomena that lie beyond our reach. The unobservable universe presents an awe-inspiring mystery, fueling our curiosity to explore further and uncover the secrets hidden in its vastness. While we may never directly observe or explore these distant realms, their existence serves as a humbling reminder of the immensity and complexity of the cosmos. The discovery that the expansion of the universe is not only ongoing but also accelerating. To comprehend this astonishing finding, we need to understand how scientists measure cosmic distances. One of the primary methods used is called the cosmic distance ladder. This ladder consists of multiple steps, each relying on different astronomical observations and techniques. At the first rung of the cosmic distance ladder, astronomers use nearby objects, such as stars and stellar clusters, whose distances can be determined accurately through various methods, including parallax and stellar brightness. By understanding the properties and behaviors of these nearby objects, scientists can calibrate the ladder and extend their measurements to more distant celestial bodies. Moving up the ladder, The next rung involves the use of Cepheid variables, a special type of pulsating star with a predictable relationship between its luminosity and pulsation period. By studying Cepheid variables in nearby galaxies, astronomers can determine their intrinsic brightness and use this information to gauge the distance to those galaxies. Further up the cosmic distance ladder, scientists employ supernovae as standard candles. These cataclysmic stellar explosions release an immense amount of energy and can be observed across vast distances. By comparing the intrinsic brightness of Type Ia supernovae, which have a consistent luminosity, with their apparent brightness, astronomers can estimate the distances to their host galaxies. Combining these various distance measuring techniques, scientists have been able to construct a comprehensive picture of cosmic distances. And it is through these measurements that the surprising revelation of an accelerating universe came to light. In the late 1990s, astronomers studying distant Type Ia supernovae made a groundbreaking discovery. They found that the observed supernovae appeared fainter than expected, indicating that the expansion of the universe was not slowing down under the influence of gravity, as previously believed, but rather accelerating. This revelation led to the concept of dark energy, a mysterious force driving the accelerated expansion of the universe. Dark energy is hypothesized to be a form of energy inherent to space itself, causing space to stretch and galaxies to move away from each other at an increasing rate over time. The exact nature of dark energy remains one of the most significant unsolved mysteries in cosmology. It is thought to constitute approximately 68% of the total energy content of the universe, with dark matter accounting for around 27% and ordinary matter making up just about 5%. The accelerating expansion of the universe challenges our previous understanding of its fate. Instead of a future where the universe slows down, eventually coming to a halt and contracting again in a big crunch, the accelerating expansion suggests a future where galaxies become increasingly separated, with the universe expanding indefinitely. This remarkable discovery not only revolutionized our understanding of the cosmos, but also opened up new avenues for exploration and research. Scientists continue to study the properties of dark energy, searching for clues that could unravel its origin and mechanisms. Dark energy is a theoretical concept that emerged from our efforts to understand the universe's behavior on the largest scales. It is postulated as a form of energy that permeates space and exerts a repulsive gravitational effect. This repulsive force counteracts the attractive force of gravity, pushing galaxies apart and causing the expansion of the universe to accelerate. The term dark energy refers to its elusive and invisible nature. It cannot be directly observed or detected through traditional astronomical methods. Instead, its existence is inferred from the observed effects it has on the universe's expansion. To grasp the concept of dark energy, let's first revisit the idea of gravity. According to Einstein's general theory of relativity, gravity is not just a force pulling objects together, it is also the curvature of space-time caused by the presence of mass and energy. Massive objects like galaxies or stars create a dent in the fabric of space-time, and other objects are influenced by this curvature, causing them to move toward the source of gravity. Now, imagine the universe filled with matter and energy. Initially, it was thought that the gravitational attraction between all the matter in the universe would eventually slow down the expansion, ultimately leading to a collapse in what is known as the Big Crunch. However, precise observations of distant supernovae revealed that the expansion of the universe is, in fact, speeding up. This unexpected discovery led scientists to propose the existence of a repulsive force, now known as dark energy, which counteracts gravity and drives the accelerated expansion. Dark energy is thought to be uniformly distributed throughout space, filling even the seemingly empty regions between galaxies. The exact nature of dark energy remains a mystery. One possibility is that it could be related to the vacuum energy or the energy inherent to empty space itself. Another hypothesis suggests the existence of a new type of field, known as a scalar field, that permeates the universe and contributes to the accelerated expansion. What makes dark energy even more perplexing is its abundance. Current theories estimate that dark energy constitutes around 68% of the total energy content of the universe, making it the dominant component. In contrast, ordinary matter, The stuff that stars, galaxies, and planets are made of accounts for just about 5% of the universe's energy content. The remaining 27% is thought to be composed of dark matter, a different mysterious substance that does not interact with light or other electromagnetic radiation. The presence of dark energy and its dominance in the cosmic energy budget raises profound questions about the ultimate fate and structure of the universe. If dark energy continues to exert its repulsive effect, it will eventually lead to a scenario called the Big Freeze or heat death, where the universe expands indefinitely, becoming increasingly cold and devoid of energy. Despite its elusiveness, scientists are actively investigating dark energy through a variety of approaches. They employ large-scale surveys of galaxies, study the cosmic microwave background radiation, and conduct precision measurements of the universe's expansion rate. These efforts aim to shed light on the nature, properties, and origin of dark energy, offering insights into one of the most intriguing puzzles of modern cosmology, the dominance of dark energy throughout cosmic history, and understand the tipping point that led to the accelerated expansion we observe today. To comprehend dark energy's dominance, we must first understand the different eras of the universe. Shortly after the Big Bang, the universe was primarily composed of radiation, consisting of photons and other energetic particles. During this era, the expansion of the universe was initially driven by the energy of radiation. As the universe expanded and cooled, matter particles, such as protons, neutrons, and electrons, began to form. This marked the transition to the matter-dominated era. During this phase, the attractive force of gravity played a significant role in shaping the universe's evolution. For a considerable period, the expansion of the universe was gradually slowing down due to the gravitational pull of matter. As galaxies and other cosmic structures formed, their gravitational interactions acted as a brake on the expansion. However, as the universe continued to evolve, dark energy gradually became more influential. Dark energy's repulsive nature started to overcome the gravitational attraction of matter, leading to a pivotal moment in cosmic history. This tipping point, often referred to as the cosmic transition or the acceleration epoch, occurred roughly 5 to 6 billion years ago. At this point, dark energy began to dominate the energy density of the universe, surpassing the combined contributions of matter and radiation. As a result, the expansion of the universe began to accelerate, overcoming the decelerating effect of gravity. The transition to dark energy domination marked a fundamental shift in the fate of the universe. Instead of a future where gravity ultimately halts the expansion and leads to a collapse, as previously thought, dark energy's dominance ensures that the universe's expansion will continue to accelerate indefinitely. The exact nature of dark energy and the reason behind its dominance remain elusive. It is believed that dark energy possesses a constant energy density, often represented by the cosmological constant or Einstein's cosmological term. This constant energy density implies that dark energy does not dilute as the universe expands, making its influence more pronounced over time. The dominance of dark energy and the acceleration of the universe's expansion have been confirmed by various independent observations, including studies of distant supernovae, the cosmic microwave background radiation, and the large-scale distribution of galaxies. Understanding the precise nature and properties of dark energy continues to be an active area of research. Scientists are developing sophisticated experiments and observing tools to probe the nature of this mysterious force and unravel its fundamental properties. As dark energy continues to exert its repulsive force, the universe's expansion will keep accelerating. Over extremely long timescales, this relentless expansion will have significant consequences for the structure of the universe. One consequence is the separation of galaxies. As the universe expands, the distance between galaxies will gradually increase. Galaxies that are currently relatively close to each other will eventually become so distant that they will no longer be visible from one another. This separation will lead to a profound isolation of galaxies, making it increasingly difficult for them to interact or exchange matter. Furthermore, as the universe expands, the wavelength of light traveling through space will stretch. This means that the energy of photons will decrease, causing light to fade. Eventually, distant galaxies will become so redshifted that their light will shift into longer wavelengths, such as infrared or even radio waves. This phenomenon will make it increasingly challenging to detect and observe galaxies that are far away. In addition, the expansion of the universe will result in the inward drawing of the cosmic horizon. The cosmic horizon represents the boundary beyond which light cannot reach us within the age of the universe. As the universe expands, the cosmic horizon gradually shrinks, limiting our ability to observe objects that lie beyond it. Ultimately, as dark energy continues to drive the accelerated expansion, the universe will reach a state known as the Big Freeze or the heat death. In this scenario, the universe will become increasingly cold and dark as galaxies move farther apart, light fades, and the cosmic horizon contracts. The expansion will eventually become so rapid that it will prevent the formation of new galaxies and stars. It is important to note that the precise details of the future fate of the universe depend on the properties of dark energy and the overall composition of the universe, including the amount of dark matter and ordinary matter. One significant event in the future of our own galaxy, the Milky Way, is the eventual merger with our neighboring galaxy, Andromeda. Approximately 4 billion years from now, the gravitational attraction between the Milky Way and Andromeda will bring them closer together. Over time, their gravitational interaction will cause them to merge, forming a new galaxy often referred to as Milkomeda. However, as the universe continues to expand and galaxies become increasingly isolated, the availability of new material for star formation will diminish. Stars are primarily formed from vast clouds of gas and dust, which collide and collapse under their own gravity. Without the replenishment of these materials, the production of new stars will gradually decline. Over the course of billions and billions of years, the existing stars and galaxies will exhaust their fuel, leading to their eventual depletion. As stars run out of hydrogen, the primary fuel for nuclear fusion, they will undergo a transformation. Smaller stars, like our Sun, will expand into red giants and then shed their outer layers, leaving behind dense remnants known as white dwarfs. Larger stars will experience more explosive transformations, such as supernovae, leaving behind remnants like neutron stars or black holes. With the depletion of stars, galaxies will transition into a state of darkness. The absence of active star formation and the fading of existing stars will result in a universe dominated by remnants, white dwarfs, neutron stars, and black holes, without new sources of light being created. As the universe continues to expand, the isolation between galaxies will persist and even intensify. Over an unimaginably vast timescale, the universe will enter an era known as the Eternal Dark Age. Galaxies will become distant islands of darkness, separated by ever-increasing expanses of void. In this era, the only remaining light will come from occasional stellar interactions, such as white dwarfs colliding or black holes capturing nearby objects. However, these occurrences will be extremely rare, resulting in an overall dim and desolate universe. It is important to note that the concept of the Eternal Dark Age represents one possible outcome based on our current understanding of the universe and its expansion. Heat death, also known as the Big Freeze or the Big Chill, is a hypothetical scenario that describes the ultimate fate of the universe. In this state, all energy exchanges cease, leading to a homogeneous, boundless void dominated by dark energy. As the universe continues to expand, dark energy's influence becomes more pronounced. Dark energy is a mysterious force responsible for the accelerating expansion of the universe, as we discussed in previous segments. It counteracts the force of gravity, driving galaxies and other cosmic structures apart. Over an extremely long timescale, dark energy's dominance increases to the point where it overcomes all other forces. As a result, the expansion of the universe continues indefinitely, with no possibility of a reversal or any significant new events occurring. In this state, the universe becomes an incredibly vast and nearly empty expanse. Galaxies, stars, and even subatomic particles are all separated by immense distances, far beyond what we can comprehend. The universe reaches a state of maximum entropy, where everything becomes uniform and devoid of any distinguishable structures. At this stage, the temperature of the universe approaches absolute zero, where there is no thermal energy left for any processes or interactions to take place. All matter and energy are evenly spread throughout space, without any localized concentrations. It becomes a cold, lifeless void. In this boundless void, no new stars form, no new structures emerge, and no new events occur. The universe becomes static and unchanging, locked in a state of eternal equilibrium. This state is what is often referred to as heat death. It's important to note that the concept of heat death is based on our current understanding of the laws of physics and the behavior of the universe. As we contemplate the grandeur of the cosmos, it's humbling to realize the sheer scale of the universe. We've discovered that our observable universe spans billions of light years, containing billions of galaxies, each with billions of stars. The numbers are staggering, and they remind us of the immensity of space and time. Yet, amidst this vastness, we find ourselves in a position of insignificance. Our planet, our solar system, and even our galaxy are but tiny specks in the cosmic tapestry. Our understanding of the universe has expanded, revealing the intricate web of connections and the patterns that govern its behavior. We have uncovered the mechanisms that drive the expansion of the universe, the influence of dark energy, and the evolution of galaxies over billions of years. We have marveled at the cosmic microwave background radiation, a relic of the early universe, and studied the formation of cosmic structures through the lens of gravitational waves. Our exploration has also raised profound questions. What lies beyond the cosmic horizon and the realms we cannot observe? Are there other universes, perhaps part of a larger multiverse? What is the nature of dark matter, the mysterious substance that eludes our direct detection? And what sparked the birth of our universe in the Big Bang? These questions remind us that there is still much we don't know, and they inspire scientists and thinkers to push the boundaries of knowledge. The cosmic scale invites us to ponder our place in the universe and to seek meaning and understanding in the face of such vastness. Ultimately, our exploration of the cosmic scale reminds us of the beauty and complexity of the natural world. The exploration of the cosmic scale has profound implications for our understanding of the universe and our place within it. By unraveling the mysteries of redshift, the expansion of space, and the dominance of dark energy, we have gained insight into the past, present, and future of the cosmos. One implication is the realization that the universe's expansion is accelerating, driven by the enigmatic force known as dark energy. This discovery challenges our previous assumptions about the fate of the universe and opens up new avenues for exploration. It suggests that the universe's expansion will continue indefinitely, leading to a future where galaxies drift further apart and new star formation becomes impossible. Understanding the nature of dark energy is a crucial area of ongoing research. Scientists are actively investigating its properties and seeking to refine our understanding of this mysterious force. Another exciting avenue of research is the study of the large-scale structure of the universe. Future surveys, such as the Large Synoptic Survey Telescope, will contribute to this endeavor by observing billions of galaxies and mapping their positions and properties. Moreover, advancements in gravitational wave astronomy offer a new window into the study of the cosmic scale. By detecting and analyzing the ripples in spacetime caused by cataclysmic events, such as merging black holes and neutron stars, scientists can explore the nature of gravity on cosmological scales and probe the universe's earliest moments. Additionally, the search for dark matter continues to be a priority in astrophysics. Dark matter, which interacts only through gravity, is thought to make up a significant portion of the universe's mass. Efforts to detect dark matter particles directly or indirectly are ongoing, with experiments conducted in deep underground laboratories and observations of galactic phenomena. As we look to the future, these investigations hold great promise for unlocking further secrets of the cosmic scale. They offer the potential to deepen our understanding of dark energy, dark matter, and the fundamental laws that govern the universe. In conclusion, our journey through the cosmic scale has broadened our horizons and left us with profound implications and exciting prospects for future investigations. Thanks for watching. If you found this video informative and interesting, please hit the like button and consider subscribing to our channel for more mind-blowing content like this. Your support means a lot to us, and it motivates us to keep creating more amazing videos for you. So, don't forget to hit that notification bell as well to stay updated on our latest uploads. Thank you again for your time, and we'll see you in the next video.